So, welcome to week 4. Uh, Today I'm going to continue with section 3.3. I'm just going to do 2 problems. It should be a short lecture. It's more about Bayes' theorem. So let me remind you what the theorem says, or the formula says, and then we'll do 2 applications. Okay, so this is section 3.3 continued. And I'm going to remind you what Bayes' theorem says again, just for the record. So if you have A and B are events, and you want to compute the conditional probability of A given that B holds, then this is something you don't know, but you can compute it by computing the probability of B given A times the probability of A over the probability of B. So in order to be able to do these computations, you need to know how to compute every term on the right-hand side. So that's the first part of it. This is really the formula. And the second part of it is the law of total probability. If you want to compute the denominator on the right-hand side, that's the probability of B. That's the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. Okay. So those are the 2 basic statements of Bayes' theorem, and then there's the general version. So you have a bunch of events, A1 through AN, and they're mutually exclusive. And they're exhaustive. So the union of all the events is the sample space, and the pairwise intersections are all empty. And then if you want to compute the probability of one of these events, A sub j given B, that's the same as the probability of B given AJ times the probability of A sub j over the probability of B. Well, that's nothing new. That's the same thing as what we did up here with A being replaced by AJ. But what's new is the law of total probability can be expressed as it's more complicated. It's a sum. I goes from 1 to n of the probability of B given A sub I times the probability of A sub I. So this is the general form of Bayes' theorem. And so what I'm going to do is I'm going to just do 2 applications. It's going to be a short lecture, as I said. So let me clear the screen. Okay, so in this problem, let me read it. It's about the conditional probability associated with email. It's estimated that 50% of all emails are spam emails. Some software has been applied to filter these spam emails before they reach your inbox. A certain brand of software claims that it can detect 99% of all spam emails. And the probability for a false positive, that is a non-spam email detected as spam, is 5%. Now, if an email is detected as spam, then what is the probability that it is in fact a non-spam email? So let's try to formulate this in using symbols. So I'm going to consider A and B events. Okay, and A is the event that an email is detected as spam. Okay, so the program thinks it's spam. B is the event that an email is actually spam. It really is spam. Okay, so what is it? So what is B complement? That is the email. An email is not spam. So these are quotation marks in case it didn't look that way. Okay, so now what is it that we want? We want to know that if an email is detected as spam, what is the probability that is in fact non-spam? So what we want is we want the event that it's not spam given that it was detected as spam. So we want the probability of that. That's what the question is asking. That's the last sentence of the problem. So now we could apply Bayes' theorem to this. So this is the probability of the other conditional probability, A given B complement times the probability of B complement over the probability of A. Okay. Now, a couple of things. First of all, we can use the law of total probability on the denominator to get the probability of A is given by the probability of A B times the probability of A plus the probability of A B complement times the probability of B complement. Okay, so now in order to do the computation, I want to compute each term on the far right side of this equation. So first of all, let's consider the event B. An email is actually B says an email is actually spam. Okay, so 50% of all emails are considered to be spam emails according to the first sentence of the question. So that says the probability of B is 0.5, which is also the probability of B complement. So we know what that is. We also know that the probability of what is the probability of A given B complement, and what is the probability of A given B? I claim we can calculate that. Let's start off with the probability of A given B. So that is the probability that if an email is actually spam, then it's detected by the program as spam. And according to the second sentence of the problem, 99% of the spam emails are detected. So the probability of A given B is 0.99. That's what that says. And then what about the probability of A given B complement? Well, B complement is saying that it's not spam, but the program A given B complement means the program is going to think you have spam even though you don't have spam. And we know that's 5% of the time, so the probability is 0.05. Now we have all the components of the right side of the formula. We can substitute it in. We get 0.05 times 0.5 over 0.99 times, what's the probability of A? Well, probability of A is the probability of an email being detected as spam. No, 1 second. I did not write the formula correctly. Let me go back and fix the problem. This should be a probability of B here. Now, what's the probability of B? That's 0.5 plus the probability of A given B complement, which we saw was 0.05, times the probability of B complement, which is 0.5. And so if you do the calculation, you get 5. I converted it to a fraction, 5 divided by 104. So that's the answer to this first question. Okay, so I'm going to do one more question today. Let me just save the screen. And let me pull up the question on a clear whiteboard. Okay, so this is example 2. Suppose we have 3 cards identical in form except that both sides of card number 1 are colored red. Both sides of card number 2 are colored black, and one side of the third card is colored red and the other side is colored black. The 3 cards are mixed up in a hat, and one card is randomly selected and put on the ground. If the upper side of the chosen card is colored red, what is the probability the other side is colored black? That's what we want to know. So I'm going to solve this problem in the following way. I'm going to give name some 3 events. Okay, so there are 3 events. So here are 3 cards. Red, red, black, black, black. And then we have a card that's one side is red and one side is black. So I'm indicating the three events. And now let RR be the event of selecting the red, red card. Let BB be the event of selecting the black, black card. And let RB be the event of selecting the card with 2 different colors, one on each side. And then let R be the event that the upturned card that we chose is red. Okay, so what is it we want? We want, if the up side of the chosen card is red, so that's the condition, we want the probability the other side is colored black. So in other words, we want the probability that we have an RB card. So that's given that the one side is red. Okay, well, this is, again, an application of Bayes' theorem. So this is, according to Bayes' theorem, the probability of red given red, black, times the probability of red, black, over the probability of red. Okay, so now we have to compute the 3 sides of the formula. I claim that the denominator, in order to compute the probability of the bottom, that's the law of total probability, we have to use we're going to have 3 terms. So first, let me rewrite the numerator of the fraction. Okay, so it's going to be probability of R given RR. So there are 3 events, and these events, not only are they mutually exclusive, but they actually are exhaustive of the entire probability space, because one of those cards is of this form. Okay, so we have P of R given RR times P of RR plus P of R given RB times P of RB plus the probability of R given BB times the probability of BB. So that's what you get. And now let's compute this. Okay, so now what's the numerator? So the numerator, the first term in the numerator is the event that if you select a card, which is given that you selected a card which is red on one side and black on the other side, what's the probability that the side you see is red? Well, that's half the time, right? Half the time you'll see that side, the red side of the card. What is the probability of RB? Well, that's the probability of drawing the RB card out of the 3 cards from the hat, so that's 1/3 of the time. Okay, so now let's figure out what the denominator is. Okay, so what is the probability of R given that you've drawn the RR card? Well, that's a probability of 1, of course. And what is the probability of drawing the RR card 1/3 of the time? What is the probability, so we now get to the second term, what is the probability given that you've drawn an RB card that you see the R side turn face up, the red side turn face up? We saw that already. That's the same thing as 1/2 the time. And then the probability of RB we saw was 1/3. And then the last term is the probability given that you have a black card. What is the probability of seeing a red upturned card, seeing that card as red on the upturn? That would be 0, right? Because it's black on both sides, it's black. So it's 0 times 1/3. Okay, so you can compute what this is, this number, and you will get 1/3. And those are the 2 applications I wanted to do today. So this is a short lecture. Have a good one.